Assalamualaikum and good morning. So sorry for this morning class session. I have to record an online material. So this will be on the content chapter 1.1 on the shear stress relations and also shear strength of the soil. So I will start my presentations on the topic contents. So it will begin with on this. Sorry for these interruptions. So let's say on the first slide of this chapter, so there are two parameters important in the elastic stress strain relation, which are Young modulus E and also the Poisson ratios. So again, if you have one relations between the sigma and the epsilon, you might find the E on the tangents of the gradient of the curve. And then also, in order to have the Poisson's ratio, this is the relations where the changes in the lateral to the changes in the longitudinal. So the negative signs indicates the samples in the compressions. And then if you have to understand what is the stress strain relations, you may see from these definitions when a material is subjected to stresses, it undergoes strains. The ratio of the stress experienced by the material at a point to the strain that is incurs is known as a modulus. Knowing the modulus of material allow us to determine the strain if the stresses can be found. However, different moduli of the body can be defined depending upon the loading and boundary conditions that the body is subjected to. So these are the things when you want to identify whether the modulus that you have it is elastic or non-elastic. So when you have a linear relations or the material undergoes in linearly, you might have a simple behavior of the material by adopting the Hooke law. So this is the simple law has been found to work quite well with most materials up to a point. Okay, again, how can we define the modulus Young or adopt the Hooke law? So looking back to this example or this what we call it, let's say you have a longitudinal sample and fixed and the boundary condition is fixed on top, and then you apply a force F, you will see that it's a increments in changes of the um, length of the material. So when you plot the force versus the elongations, this will be the behavior of the material that is happen linearly. I mean that when you have a force 50 and then the elongation is a 2 millimeter changes, and then you increase the force to 100 to maximum 200, you will see that the elongation also increase linearly by the stress increase. So the stress strain relation given by formula sigma is equal to E times an epsilon, where the E is the Young's modulus. So remember again, what is the stress? Stress is a force over to cross-sectional area E, while strain epsilon is equal to the change in material to the original shape, which means that the delta is equal to final length minus original length. Okay, this is similar if an elastic body is stressed in the x direction by a normal stress, sigma x. And how does this material experience in the stress itself and also in epsilon or the strain in the x direction, y direction, and z direction. So for this case, due to the force only in horizontal, in lateral directions, that's why the sigma y and sigma z equal to 0. So similarly to here, also this one, and you can see that how the two normal string components are derived in the epsilon y and epsilon z directions, and also the effect of shear stress is to cause a shear strain. Okay, this is when we apply the relation stress strain uh, in the matrix, for example, where we have the Poisson ratio. We also have the Young modulus. We also want another modulus. We call it as a shear modulus. Also, we can express the stress in terms of strain as follow. So this will be the easier way to represent the stress and strain relation. Okay, where the A is equal to E over 1 times to nu times 1 plus nu. Also, in the metric notation, it can be shown or it can be written by this equation 31. In most cases, all the problems are analyzed in two dimensions, whether it is in the plane stress or in the plane strain. Okay, this is a case where you can analyze in the plane stress analysis. A plane stress analysis is one in which the stresses on two of the faces is 0. If we consider the anti-plane faces as the stress-free faces, then we effectively set sigma z, tau yz, tau zs equal to 0. By setting the sigma z equal to 0, in equation 30 just now, leads to the final equations of the sigma, in the epsilon z. And also, when we substitute equation 45 into the first two rows of equation 30, leads to the sigma x is equal to this one, which simplifies into sigma x is equal to E over 1 minus nu square times dengan epsilon x plus dengan nu times dengan epsilon y. So when we present it in a matrix in two-dimensional plane stress conditions, and the equation 33G is derived. So the plane stress analysis are often applied to problems relating to thin plates and structural members wherein out of plane stresses cannot build